Hi gentlemen, and welcome to today's lesson on ionic and covalent bonding. We're going to continue to focus on ionic and covalent bonding, and today specifically we want to talk about their properties, both physical and chemical. Okay, so let's quickly review here. Let's talk about ionic bonds. If you remember, they form between a metal and a non-metal. So the metals, again, you find them on the left-hand side of the periodic table, tend to give up electrons, where non-metals you tend to find them on the right-hand side of the periodic table, and they take on electrons, becoming negative in this case. Okay? So you're going to find that one or more of these valence electrons are transferred from the metal to the non-metal. So the metal becomes positive again. Now you've lost an electron, you have an extra proton. Right? It becomes a cation. Or a non-metal becomes a negative ion. It gains an electron, so now it has more electrons than protons, and it becomes an anion. The ionic compounds don't actually form distinct molecules like covalent bonds do. Instead, we get these large crystal structures, which we call crystal lattices. We actually create the formula for that metal by paring it down to its smallest ratio. So basically taking it down to its lowest common denominator. So what that looks like is this. Right? So you get this crystal lattice where you have your cation and your anions all attracted to each other, right? Positive and negative, drawn together, creating this crystal lattice. And we can see here in this case, I have my 6 chlorines and my 6 sodiums, right? So this is a 1-to-1 ratio. So this pairs down to NaCl, which we call the formula unit of an ionic compound. Okay? And again, how we hold them together, they're held together by this balance between the electrostatic attractions, right? The positive, the negative, attracted together. And there is a bit of a balance there, right? It's also repulsion between electrons of each ion, as well as the protons. Basically, you're going to see that it's arranged so each ion has the greatest number of oppositely charged ions surrounding it. Okay, so they're trying to avoid, and you can see again in this picture, you want to avoid having too many of the same charge side by side. Okay, so we're trying to keep those positive charges as far away from each other, and the negative charges away from each other. Okay, and that's your crystal lattice, that's your ionic bond. Covalent bonds, remember, we're talking about 2 non-metallic atoms. Okay, generally you see them, we often see diatomic molecules where you have 2 atoms of the same or a different element. We also see polyatomic molecules where you get many more, up to 3 or even more than 3 atoms of the same or different elements combining. Okay, so now you're talking about this this attraction between 2 nuclei for 1 or more of shared pairs of electrons. So again, we'll go back and take a look at covalent bonding. You see now there's an electron for each of these protons, but there's that strong attraction. So now the electron is drawn by both of these protons, creating this bond. Okay, and if we see 1 pair of shared electrons, we call it a single bond. If you have 2 shared pairs, you have a double bond, and 3 shared pairs, you have a triple bond. Okay, so the bond strength increases as the number of paired shares of electrons increases. So you're going to see triple bonds are much, much stronger than a single bond. Double bonds kind of fall in the middle there. Okay, so what does all this mean in terms of properties? Well, let's take a look. Ionic compounds will find that they do not conduct electricity when they're in the solid state. Okay, so when you're dealing with the crystal lattice, you're not going to see the conductivity of electrolytes. But when you dissolve them in water, such as this, okay, so if your solid dissolves in water, now you have these free-floating ions. Okay, and in this case, this is now an aqueous solution. This will now conduct electricity, and we call that an electrolyte. Okay. You'll find that they also have extremely high melting points, again because of that very strong attraction. Okay, all of the atoms or all the ions involved in an ionic compound are attracted by intramolecular forces, which are very, very strong. Okay, and so it's hard to break that down and melt it and pull them apart. Okay, again, we just saw they're soluble in water, and they tend to be brittle and are crushed quite easily. Think about salt. Okay, table salt, fairly brittle, crushes up very, very hard, but it will dissolve in water and will conduct electricity. Okay. Physical properties of molecular compounds, on the other hand, now you're talking about a much lower melting point. Okay. Now, because the attractions between molecules is much weaker, the attraction now is within the molecule much more so than it is between molecules. So if you were to bring, see, this is we call this a hydrogen atom here, right? We have these two hydrogen molecules, sorry, the two hydrogen atoms strongly attracted, okay, to each other. But if you brought another molecule along, the attraction between the two wouldn't be as strong. So it's much easier to break this up into a much less dense substance, like a gas or a liquid. Okay? Most of them do not conduct electricity in either the solid or liquid state, okay, because they don't have a charge. Okay, and the charge allows electricity or electrons to pass from thing to thing. So that from atom to or electron, ion, or atom to atom. Okay, so in an ionic compound, you have these free-floating ions available for electrons to pass from one to the other. That's not the case in molecular compounds, so they're not likely to conduct electricity. Some are slightly soluble in water, but generally you'll find that these molecular compounds are insoluble in water. And so you won't see, they'll tend to stay together. If it's a solid, it'll stay solid. And they are often soft and can be waxy or flexible. So it's sort of the opposite here in terms of ionic compound. Right? You find the table salt very, very hard. Your molecular compounds much softer and flexible. Okay, thank you for your time, gentlemen.